French chemist Louis Chatelier in the year 1984 observed that if any system at equilibrium is disturbed by a change in concentration, pressure, or temperature, the system will shift in such a way to oppose the change. We shall use the following imaginary reaction where A and B are reacting to form products C and D. We are assuming that at 100 degrees Celsius, the equilibrium constant for this reaction is 50. It is equal to the product of the concentrations of A and B raised to their respective stoichiometric coefficients divided by the product of the concentrations of C and D raised to their specific stoichiometric coefficients. Also, we'll use Luchat's principle to enable us to predict in which direction this equilibrium will shift if changes in concentrations of products and reactants are made at 100 degrees Celsius. In this first scenario, the concentration of reactant B is increased. From a mathematical perspective, if that happens, then the equilibrium constant increases, and that cannot happen at a constant temperature. Note that for any reaction, the equilibrium constant does not change as long as the temperature remains constant. The only thing that will change the equilibrium constant is a change in temperature. So, to restore the equilibrium, the system will shift from right to left to make more products. So we're increasing that according to Luchat's principle. To remove the effect of that, more of A will react with B to give you some C and D until this value is restored. From the mathematical perspective, we're decreasing the top and increasing the bottom. That means you're removing reactants and making more products. So we're going to read the notes that we make here. If either the concentrations of A or B is increased, to restore the equilibrium, the system will shift to the right, making more products. In this second scenario, the product C is increased. From a mathematical perspective, if we increase the denominator, then the equilibrium constant should go down. And therefore, to restore its value, the equilibrium will shift from the right to the left. In other words, we're removing species from here and we push them at the top, such that this value becomes restored. This is the conclusion that is made. If either the concentrations of C or D is increased, to restore the equilibrium, the system will shift to the left, making more reactants. In this third scenario, we are reducing the concentration of reactant A. From a mathematical viewpoint, that will make the equilibrium constant get less, and that cannot happen. As such, to restore the equilibrium, we're going to have species from the denominator being changed to those of the numerator. So we're taking products and we're making reactants. So if we remove this guy, then product will react to restore that, to try to restore that. So make a general statement then. The same thing is going to happen if you reduce the concentration of B. If either the concentrations of A or B is decreased, to restore the equilibrium, the system will shift to the left, making more reactants. And finally, in this fourth scenario, we are decreasing the concentration of product D. What do you think will happen? To restore it, the equilibrium will shift to the right. So from a mathematical perspective, if we reduce that, then this value should increase, and that can't happen. And therefore, you're going to get species from the numerator reacting to form those that make up the denominator. So what is happening? You're getting A and B reacting to give more of C and D. So this equilibrium is going to shift in this direction. If either the concentrations of C or D is decreased, to restore the equilibrium, the system will shift to the right, making more products. So generally speaking, according to Luchat's principle, if a system is at equilibrium and one entity is reduced, the system will shift in a direction to restore it. If an entity is increased, it will shift in a direction to reduce it. Now we will use the reaction between sulfur dioxide and oxygen to give sulfur trioxide to illustrate how equilibrium shifts happen when changes in concentrations of reactants and products are made. We will also show graphically how these equilibrium shifts happen with time. So these are the initial concentrations of reactants and products. On the equilibrium constant expression is written as this. In this first example, we are increasing the concentration of sulfur dioxide. That's the initial concentration, and this represents the increase in concentration. So what do you think will happen when you increase the concentration of sulfur dioxide? According to Luchat's principle, to reduce the effect of this increase in sulfur dioxide concentration, some oxygen will react with some of it to form some amount of sulfur trioxide. The equilibrium will thus shift to the right. We have increased the concentration here, and we now have to react some of that with oxygen to form some sulfur trioxide. Note how, because the stoichiometric coefficients of sulfur dioxide and sulfur trioxide are the same, you're going to find that equal number of particles of sulfur dioxide will produce an equal number of particles of sulfur trioxide, but they'll only be reacted with half that quantity of oxygen in every case because of this stoichiometric coefficient of 1, which is only half of what these are. So you're showing here how we have increased the sulfur dioxide concentration and how to shift the equilibrium to the right, some amount of oxygen is reacting with some amount of sulfur dioxide to give you some sulfur trioxide. The equilibrium shifts to the right. Of course, these were the initial concentrations at equilibrium. Now this new graph here is showing you the effect of increasing the concentration of sulfur dioxide. So note a number of things. One, these were the initial equilibrium concentrations of the reactants and products, and we have increased the concentration of sulfur dioxide. Now note this, whenever you increase the concentration of something, there is a sudden spike. It doesn't take any time for that to happen. So that was the initial concentration, that's a new concentration. But to restore the equilibrium, it takes some time. That's why you're not going to see a spike going backwards. You're going to see a little curve going on like that. I want you to see how the system goes to reduce back the amount of sulfur dioxide, but it does not reduce it to its original concentration. So this is the original concentration after we've increased the sulfur dioxide. So look what happens. Only some quantity of it gets reacted with oxygen, but we still have that excess there. So let me go back and show you what was the original concentration. That was the original concentration. That was a new concentration. But we have only removed a part of that. So the concentration of sulfur dioxide still remains somewhat higher than its original concentration. Look else what is happening. While sulfur dioxide is being removed, simultaneously sulfur trioxide is being created, and of course some amount of oxygen gets removed. So you can see that the rate at which the sulfur dioxide is being removed is equal to the same rate at which sulfur trioxide is being reformed because of their stoichiometric coefficient, and this oxygen is only going to be half of that. And there's some notes that I've made here. You can pause the video and read those. We'll now be decreasing the concentration of sulfur trioxide. So these are the initial concentrations at equilibrium, but now we are decreasing the concentration of sulfur trioxide. That is what it was before, and this is a new concentration here. So according to Luchat's principle, if we remove something, what's going to happen? The system will shift in a direction so as to replace it. So to reduce the effect of this decrease in sulfur trioxide concentration, some amount of oxygen would react with some sulfur dioxide to replace it. So that was the initial concentrations of sulfur dioxide and oxygen. Some of these will now start to react. So you're seeing two particles there are reacting one particle here to give the same two particles here. So the equilibrium is shifted to the right. How do you think these graphs will look? We have decreased suddenly the concentration of sulfur trioxide. You're going to see the opposite of what happened before. You're going to see a spike downwards. What do you think will happen here? These are getting reduced. See? So here we are reducing stuff, so it's a spike downwards. But then the system tries to replace it, but it doesn't get replaced to its original concentration. That was the original concentration. This is the reduced here, but now you can see it gets partially restored. But the concentrations of sulfur dioxide and oxygen get reduced. This one gets reduced by the same quantity that that one gets increased, but this is only always getting reduced by half. And I wrote some things there. You can read that, pause the video and read that. Finally, we're going to decrease the concentration of oxygen. So these are the initial concentrations, and this graph depicts how they are at equilibrium. So we're removing some oxygen. What do you think is going to happen according to Luchat's principle? To restore it, the equilibrium will shift in that direction. To do that, some sulfur trioxide will decompose to try to restore the oxygen. And of course, we're going to get some amount of sulfur dioxide being produced also. And that is depicted here. Some amount of that is decomposing to produce oxygen and some sulfur dioxide. What do you think these graphs are going to look like? We are reducing the concentration of oxygen, so you should see a spike downwards. The system tries to restore it, but it does not go back to its original concentration here. See, that was what it was before. Now this is what it is in the end. But what do you think will happen here? Look what is happening. The sulfur trioxide concentration gets less with time because it breaks down to try to restore the oxygen. Again, I've written some things there for you to see. Luchat's principle enables us to predict in which direction an equilibrium will shift if any change in property is made with respect to that equilibrium. However, it does not explain why these shifts happen. It is reaction kinetics that enable us to understand why these shifts happen. Let's take the example of increasing the concentration of sulfur dioxide as we've done before to show how reaction kinetics can enable us to understand why the equilibrium shifted to the right. When the concentration of any reactant is increased, as happened in this case, temporarily the rate of the forward reaction becomes greater than the rate of the reverse reaction. This is so because there is now a greater frequency of collision between the particles of the reactants than there is between those of the products. This will not continue forever because the concentrations of the products will eventually increase, and that will increase the backward rate. So eventually equilibrium is restored when the forward rate becomes equal to the backward rate. In this case, we are reducing the concentration of a product. Again, the forward rate compared to the backward rate gets temporarily greater because the frequency of collision of the product molecules become less than that of the reactant molecules. As such, the equilibrium will shift in that direction until again equilibrium is restored because the concentrations of these will eventually increase and the backward rate will eventually pick up back again to be equal to the forward rate. In this case, we will reduce the concentration of oxygen temporarily because you're having fewer molecules on this side. You have a greater frequency of collision here. As such, the reverse rate temporarily gets bigger than the forward rate. Of course, eventually, as the concentration of the reactants increase, the forward rate will pick up until it becomes equal to the reverse rate, and then these equilibrium here will be restored. This brings us to Louchat's principle and pressure changes. Recall that the pressure of a fixed mass of gas is affected by the following three factors: temperature, number of moles of gas particles, and the volume of the container in which the gas is contained. And all of that is factored into this ideal gas equation, which says that PV is equal to nRT, or P is equal to nRT divided by V. According to that, the pressure is inversely proportional to the volume, directly proportional to the temperature, and directly proportional to the number of moles of gas particles present. So now we're looking at how the number of gas particles affects the pressure. Cylinder A is having a certain number of particles, and cylinder B shows an increased number of particles. If you look at the ideal gas equation, you can see that all of these remains constant, but now we have increased the number of moles of particles. As such, the pressure here will increase, so we can say that P2 is greater than P1 by virtue of the number of particles. So two things. If we increase the number of particles, the pressure increases. Conversely, we can say that if we reduce the number of particles, the pressure decreases. So an increase of number of particles increases the pressure. A decrease in the number of particles decreases the pressure. What do you think will happen if you add an inert gas? Number of red particles are the same in both cases, but we put in some blue particles that represent inert gases. Of course, according to Dalton's law of partial pressure, the pressure inside here is going to be greater than the pressure inside here by virtue of the larger number of particles, regardless of what type of particles, okay, as long as these do not react with each other. Now we will look at effect of volume changes and pressure. So this has a fixed number of particles, but we are decreasing the volume by pressing that plunge in a little bit more. So if we look at the ideal gas equation, all of these remain constant, but now we are decreasing V. Mathematically, if we decrease that, that gets higher, okay? So we can simply say in this case that P2 will be greater than P1. Another way of increasing the pressure of gas in a cylinder is by decreasing the volume. If we increase the volume, the pressure gets less. We'll now look at the effect of temperature changes. Cylinder A has a certain pressure at a certain temperature. Cylinder B has the same number of particles, but the temperature there has been increased, and you can see here T is directly proportional to P. As such, you'll expect the pressure of the gas in this cylinder to be greater than inside there. And this brings us to an important industrial compound, which is ammonia. We look at the synthesis of ammonia. The synthesis of ammonia is an important process, since ammonia is crucial in making other nitrogenous compounds such as fertilizers. So what we are seeing here in the synthesis of ammonia, we are having 3 moles of hydrogen reacting with 1 mole of nitrogen to produce 2 moles of ammonia. Note that every molecule of hydrogen is considered to be a particle, a molecule of nitrogen is considered a single particle, and this entire ammonia molecule is also considered to be a particle. So we can see that 4 particles are reacting to give 2 particles. The equilibrium constant expression for this is written as follows. Because of this ratio by which hydrogen is reacting with nitrogen to give ammonia, scientists make use of this difference in mole ratios to pressurize the gases to favor the production of ammonia. And let us see how that happens. Why, if we push the plunger in that direction, it favors the production of ammonia? Remember, one of the ways by which the pressure of a gas is increased is by decreasing its volume. So by decreasing the volume here, we are increasing the pressure. And according to Louchat's principle, the system will shift in a direction to reduce the pressure. And how do we reduce pressure again? We can also reduce the pressure of a gas by reducing the number of particles inside. you have a greater number of particles here, there's a certain pressure. When you reduce the number of particles, the pressure gets less. So in this case, what you're doing happen? Because you're increasing the pressure, the system will shift in a direction that makes fewer number of particles. So you have 4 particles that are reacting here to give you 2 particles. So definitely the system will shift in that direction there to make ammonia, wherein you have lesser particles being formed. So when you squeeze these gases more, they allow 4 particles to make 2 particles. As such, the production of ammonia will increase. Now there's an interesting thing that happens in the synthesis of ammonia. This reaction is exothermic and its equilibrium constant is written as such. We want to see how temperature changes affect this equilibrium. We'll use heat as a product, as that will facilitate us in predicting which direction shifts will happen when the temperature of this reaction is changed. So let's see what happens if the temperature is raised. If you raise the temperature, it's like adding a product. So according to Le Chat's principle, the reaction will shift in that direction. If it shifts in that direction, that means there's breaking up of ammonia. Ammonia will decompose to give you nitrogen and hydrogen. That does not favor the production of ammonia. Another thing that's going to happen, because you're reducing the concentration of ammonia, you're making more of these guys, the equilibrium constant will get less. So there'll be less ammonia in the equilibrium mixture. But look at this. Since the reaction is taking place at a higher temperature, the rate at which the equilibrium is attained is faster. Let's see what happens when you lower the temperature. According to Le Chat's principle, we are removing heat, we are removing this guy. This system will try to go in the direction to replace it. So what's going to happen? You're going to have more hydrogen and nitrogen reacting with each other to give you ammonia. The equilibrium constant now will increase because you're creating more of that. But it will take a long time for this equilibrium to be established. So there's a temperature dilemma here. So I'll read that for you. While a rise in temperature increases the rate of production of ammonia, which is what is desirable, unfortunately causes a decomposition of it. While a lowering of the temperature increases its equilibrium yield, the rate at which equilibrium is attained is slow. Thus, scientists have resorted to using a suitable temperature that will neither be too low to compromise the rate of production of ammonia, nor too high to cause much of it to decompose. The use of very high pressure and suitable catalysts have mitigated this dilemma to a considerable degree. One demonstration that I used to show my students to show the effect on equilibrium concentration was the one that involved the equilibrium between nitrogen dioxide and dinitrogen tetroxide. Nitrogen dioxide is a brown gas, while dinitrogen tetroxide is colorless. At room temperature, a glass tube containing this equilibrium here has a color like this. That means that the equilibrium is more towards the left because of the predominance of the brownish color. To demonstrate the effects of temperature changes on this equilibrium, I will use 2 of these tubes filled with these gases at equilibrium. One of the tubes will be left at room temperature that had this color, and the other one will be placed in a freezer. Periodically, the one in the freezer will be observed and the following color changes will be produced. So as the tube is cooled, gradually its color changed from dark brown to colorless. Soon after the test tube was taken out of the freezer and it started to heat up, it reversed in color changes. From colorless, it gradually returned to its original brown color, like this one here that was used as a control. How do we use Le Chat's principle to explain these equilibrium shifts? Since the reaction is exothermic, as it was cooled, heat being a product was removed. So, to restore the heat, the equilibrium shifted to the right during this process. The NO2 gas, which is brown, was changed to colorless dinitrogen tetroxide that is colorless. When the tube was given heat as it was taken out of the deep freeze, since heat was added, which is a product, to remove the heat, the equilibrium shifted from right to left, changing colorless dinitrogen tetroxide to brown nitrogen dioxide. And that is how we use Luchat's principle to explain these color changes. One point I forgot to make with regard to adding an inert gas to this gaseous system at equilibrium. If an inert gas is added to this mixture, it does increase the pressure. But will it cause an equilibrium shift to the right? The answer is no. This is because the gas being inert does not influence the rate of the reaction. When the pressure of the gas in this mixture was increased due to a decrease in the volume, the concentrations of hydrogen and nitrogen increased to a greater degree when compared to the increase in concentration of ammonia. As such, the frequency of collision between nitrogen and hydrogen was greater than the frequency of collision between ammonia molecules. As such, the fold rate temporarily became greater than the fold rate, and that is why there was an equilibrium shift to the right. Inert gases, because they are not active reactants, are not capable of influencing an equilibrium shift. However, they do cause an increase in pressure if they're inserted into the gas mixture.